Okay, so let's take a look at 3.2 periodic trends. This topic is about the patterns that we can see within the periodic table. For each of the patterns or trends that we talk about in this class, you need to be able to do three things. You need to provide a definition for what the trend is about. You need to explain what happens to the trend as you go down the periodic table and across the periodic table. And lastly, you need to explain why the trend happens based on the arrangement of subatomic particles. Okay? So let's take a look at our first trend. Let's talk about atomic radius. So atomic radius talks about how big atoms are. To measure it, we basically take the center of the atom, the nucleus, and we measure the distance to the furthest electron, and that is known as the atomic radius. As we go down the periodic table, the atomic radius increases. So we get larger and larger elements as we go down the periodic table. As we go across the periodic table, staying in one period, the size of my elements actually decreases. So you need to be able to describe why that happens, which is what we're going to look at now. To do that, let's select two elements. So let's select this one right here. So this is lithium, and this one right here, this is cesium. So if we were to draw lithium and cesium, we know that the electron configuration of lithium is 1s2 2s1. So lithium has 3 electrons, 2 located in the first energy level and 1 located in the second energy level. So if we were to draw what it looks like, it would basically have 2 energy levels, 1, 2, surrounded by a nucleus, or surrounding a positively charged nucleus. On the other hand, if we were to take a look at cesium, the electron configuration of cesium, which I'm definitely not going to draw out completely because it's quite long, is exactly the same as the electron configuration of xenon, and the final electron is in the 6th energy level. Okay, so hopefully you can notice the difference. Here my furthest electron is in the 2nd energy level, and here my furthest electron is in the 6th. So let's draw that. So it would be 1, 2, 3, 4, 5, 6. So hopefully you can see that because cesium just has so many more occupied energy levels, occupied energy shells, it's much, much bigger. And that's the same idea that happens as we go down the group. Each element going down the group has one more occupied energy level. So let's write that down before we forget. So as we go down a group, what happens is we increase the number of energy shells. Okay, an increase in the number of shells means that the furthest electron is farther away. There's a greater distance to the nucleus. So again, this distance is smaller than this distance. Okay, which means that as you go down a group, because of the further distance from the nucleus, our atomic radius increases. Sorry, this should be the other way around. I just noticed that. So this should be atomic radius. Okay. Now let's get a little bit trickier. As we go across a period, our elements get smaller. So this one's a little tricky. Let's compare lithium with fluorine. So they're in the same group, same period, but fluorine is much smaller. Let's figure out why. So let's compare lithium and fluorine in the same period. I'm going to do the shortened electron configuration. So we know that lithium has exactly the same electron configuration as helium with 1 extra electron, and fluorine has exactly the same configuration as helium with 7 extra electrons. Okay? Now there's some things that you need to notice. You should notice that the outermost electrons are all in the second energy level. So whether we're talking about lithium or fluorine, they're all in the second energy level. So there's no difference in the number of occupied shells. Okay, let's write that down. So, oops. So I was saying that there's the same number of shells that are occupied. Okay? However, as we go across from left to right, hopefully you'll remember that we have more protons. So each new element, lithium, beryllium, boron, carbon, has a greater number of protons in the nucleus. That greater number of protons in the nucleus means that these protons are better able to attract the outermost electrons, which means that the distance from the nucleus between the outermost electrons and the nucleus is decreased. So the decrease in distance between the protons and electrons, greater attraction between the protons and electrons, and that results in a decreasing of atomic radius as we go across the period. So again, there is the same number of shells as we go across the period. How do we know? Both lithium and fluorine only have electrons in the second energy shell. And so, even though it's the same number of shells, we have more protons, which means that there's a greater attraction between the protons in the nucleus and the valence electrons, a decreased distance, and a decreased atomic radius.